Good afternoon, everyone. At this moment, I will be discussing the chapter 7, specifically the chapter 7, 7.3, which is the SYLOW's theorem. Since this course is all about the abstract algebra, this is more on about the group theory. So we need first to understand and comprehend what is a group and what is a subgroup. How can we determine that a certain group is a really group, and also how can we determine the particular subgroup is a really subgroup in a said group? So as presented in my second slide to show you how these groups and subgroups can be identified. So now let us talk about what is a group. So how can we determine that a certain group is a really group? So here we have the definition of a group. A group consists of non-empty set G together with a binary operation star. The following properties hold. So meaning the group consists of non-empty set G. So meaning a group is not an empty set. So meaning G consists or comprises of elements or element, no, together with a binary operation star. The binary operation star here, it will be represented, or it could be multiplication or addition, such that the following properties hold. So in defining and determining the group, no, if we determine that a certain group is really a group, we have four properties or characteristics that we can consider that if that certain group, if these four characteristics or properties are satisfied in a certain group, so that time, so we can conclude that a certain group is a really group. So here we have the properties. The property 1, closure. The definition of closure: if A, B belongs to the group G, then A star B also belongs in a group G. So meaning in a certain group we have two elements. If you are going to perform the two elements using the binary operation, or what is the binary operation being used in a group? So if we are going to perform the two elements, or A star B, for example, if our group is use binary operation of addition, so meaning A plus B is also belongs to the group G. So that is the meaning of closure. How about the associativity? For all A, B, C belongs to the group G, we have the A star open and close parenthesis of B star C is equal to the open and close parenthesis A star B star C. So if we are going to perform these three elements, the outcome of this one is also similar in this one. So that is the associativity. So later I will be giving an example for us to better understand what I'm talking about here. So the third one, identity. There exists an element A is in group G, such that for any A belongs to the group G, A star A is equal to the A star A is equals to A. So meaning E here is the identity. Then now, so it depends upon what is the binary operation being used in a certain group. If the group use a binary operation of addition, so the identity of addition is 0. Then the identity of multiplication is 1. For example, so we have the 3. So what is the number that we can add in a number 3? We have the result is the identity, which is 3. So 0. How about in a multiplication? If the certain group using a binary operation of multiplication, if for example 3, what is the number that we multiplied in 3 gives back the identity, which is 3. So 3 times 1 is equals to 3. So that is why the identity of the identity of the multiplication is equal to 1, and the identity of addition is that 0. So we are now in the last property of group, inverse or inverses. For any A is in a group G, there exists an element E inverse also belongs in a group G such that A star E inverse is equal to, parihara daw siya sa E inverse star A is equal to the identity. So meaning, if we're going to perform the inverse, if there's an element, for example, 3, so then the binary operation that being used in a certain group is addition. So what is the inverse of 3 that gives back to the identity? So the identity of addition is 0. So what is the number that, for example, 3, no? What is the 3? So what is the possible number that if we're going to add, we have the result 0. So 3 is negative. The inverse of positive 3 is equal to negative 3 because positive 3 plus negative 3 is equal to 0. That is the meaning of inverse. So how about the multiplication if the certain group use binary under the binary operation of multiplication? So for example sa 3, so the inverse of 3 is the reciprocal niya. So if we're going to perform the inverse in the multiplication, we give back the identity ang result niya. So the identity of the multiplication is, since 1 man siya, so the so for example 3, so 3 here, so 3 ni siya ang atong A, so A star. So since our star here is we use the specific binary operation which is multiplication, so 3 times the inverse of 3, which is 1 over 3. So 3 times 1 equals 3 over 3 is equal to 1. So that is the result, is the identity. That is 1. We gives back if we're going to perform the two elements, so the result, so the outcome is the identity of multiplication, which is a 1. So let us proceed so later I will be giving an example of this the group after discuss the subgroup, because even though this group and subgroup are dili siya covered to my topic, so since this is length in my topic, so even though this particular topic, group and subgroups, has been discussed from the previous chapter, so in my case, at this time, so I'm going to expound and explore that how can we determine the group, no? How can we determine that certain group is a really group, and how can we determine that subgroup, no? What are the characteristics of the subgroup that we can consider that a certain group is a really subgroup in a group. So meaning sa subgroup is nasiya'y group nga ang subgroup nag-contains of elements nga naa sa group. That is why it is called a subgroup. So let us proceed in the subgroup. So further, we have the definition of subgroup. After I discuss the definition of subgroup, so I will give an example of a group, then subgroup na sadpod. So meaning, definition of a subgroup. If H is a non-empty subset of a group G, so meaning H is not an empty set, is not an empty subset of a group G. So meaning H contains an elements, but for all elements in group H is also belongs in a group G. So that is called H is a subset. H is a non-empty subset of a group G. So then H is a subgroup of G if H is a group under the same operation as G. So meaning, so we can say that subgroup H, we can say that the group H is a subgroup of a group G if kini nga H daw is use the same binary operation as what the binary operation being used in a group G. So that is the definition of a subgroup. If naghimo siya og nasa grupo ni siya but in line sa binary operation nga as what the binary operation being used in a group G. So right? So now we have three important points, no? Kini importante jud kini. We have three important points that we can consider if these three important points or characteristics are satisfied in a group. So that is that time we can say that a group is a subgroup of sa kinadakan nga grupo. So now, so the first one point, the first one important point is that H is a subset of J. So meaning H is a subset of J. For all element in H na apo ni J. That is the meaning, no? So H is a group. So maybe since it's a subgroup siya, so H grupo pod siya but subgroup siya sa J. So H is a subgroup. So as I said a while ago, we have four important points nga a certain group, we can consider that a certain group is a really group, no? The first one property is that closure. The second one, associativity. The third one is that the identity. No, it depends upon what is the binary operation of the identity. If multiplication is 1 and the addition is 0, H and J use the binary operation. Use the same binary operation as what is stated here in the definition, no? If G it's a group under the same operation as J. So meaning same operation, say binary operation same ra na sila unsa ang binary operation nga ginagamit nila. For example here. We have the example G4. Set of integers modulo 4. So meaning this group containing 4 elements, the set of integers 0, 1, 2, 3, no? In determining or testing the certain group is a really group by using the Keles table, or shall we say the Keles table. Dayon, by using the Keles table, we can determine if a certain group is a really group. Din kani nga H mo ni ang subgroup nga kini mo ni ang subgroup din diri sa grupo. H is a subgroup of a group G, no? The atong subgroup daw is 0, 2. They are going to our objective here is that to determine this subgroup is really this kini nga grupo nga is really subgroup in a group G, because kini grupo gyapon ni siya but nag-align ni siya sa as what the binary operation nga gigamit sa group G nga kinadak-an nga grupo. Kini basilbi kani sa for all elements in H also belongs in the group G. Muna gitawag sa subgroup. So by using the Keles table, as I said a while ago, mo yung Keles table niya. So how can we perform in the Keles table using the 4 elements in the set of integers modulo 4 here? So I'm going to solve this one, no? Can you take a look in the screen? So we have the group G mod 4, set of integers modulo 4, 0, 1, 2, 3. Dito ato na siyang itas kung ato na perform using the Keles table, no? Kung ma-identify nato na siya kung group gida siya tinuod. Under this group so this group is under the binary operation of addition plus ni siya. Dili na siya times, no? Natay duha mo ka pilian ang atong binary operation. It could be multiplication or an addition, but this time we use the addition. Siya 0, 1, 2, 3. This is the original elements 0, 1, 2, and 3. 0 plus 0 is equal to 0. 0 plus 1 equals 1. 0 plus 2 equals 2. 0 plus 3 equals 3. 1 plus 0 equals 1, 1 plus 2, 1 plus 1 equals 2, 1 plus 2 equals 3, 1 plus 3 is equal to 4, but modulo 4 mo na nga 0 na siya. 2 plus 0 equals 2, 2 plus 1 equals 3, 2 plus 4 equals 4 modulo 4, 0 siya. 2 plus 2 plus 3 equals 5, but modulo 4, 1 na siya. 3 plusan og 0, 3 na siya. 3 plusan og 1, 4 modulo 4, 0 na siya. 3 plus 2 equals 5, modulo 4, 1 na siya. 3 plus 3 equals 6, but modulo 4 equals 2. So meaning we have the four, as I said a while ago, we have 4 elements. We have 4 elements. We have 4 elements. No. We have 4 properties that we can consider that a certain group is a really group. So the first one is closure. So atong una is closure. Unsa ang closure giingon niya? Natay element nga duha nga belong sa grupo. Atong group ani is G mod 4 mo na atong grupo. Dayon kini kon A star B is also belongs na daw na grupo. So meaning our star here, since we use the specific the binary operation which is addition, so meaning magkuha ta og we are going to select the two elements out from our group. Then it should be coming from in the original group. So meaning, so natay duha ka elements diri sila asa 0 og 1, 0 og 1 atong kaon nga elements. Dayon mo ni ato ang duha ka elements nga 0 ug 1. Dayon are going to perform the using the binary operation since this is addition. So 0 plusan daw og 1, unsa daw resulta niya is naa daw siya. According to the definition of closure, ano to kini mo ni definition, duha ka elements nga gikan sa group. Ako to na i-perform ang duha ka elements. Ang iyang result daw is naragyapon sa grupo. So here, so we have the example no, 0 plus 1 mo nitong duha ka elements nga gikan sa atong the set of integers modulo 4 mo nitong group. Dayon 0 plus 1 dapat dili ta mingon nga magbuot-buot kay dapat we always basing in the what is the result or what is the outcome in our Keyless table. Dili ta mag-base sa Keyless table kini. Dili ta mag-base. So meaning 0 plus 1, so 0 plusan daw og 1 is equal to 1. So 1 daw siya ang result niya. 1 bigis pud ta tinuod og bisan dili siya maglantaw sa Keyless table, but dili tanan nga elements, dili tanan nga situation. 0 plus 1 plus 1 is equal to 1. So ang 1 daw is element daw ang 1 daw is element daw sa grupo. Muna ang bato sa closure. So meaning element daw sa grupo. So, tinuod siya. Di ba atong group ay kalibog nga G nga got ni o dili kay G but for kasi pariharan na sila is same group ni siya. Kini siya consider as group lang ni siya, grupo ni siya, pero grupo ni siya mo nag-represent nga G, capital letter G. So 1 daw naa daw sa group nga G mod 4. Di ba naa ang 1? So mo na sa tinuod. So we have the closure here. We have the closure here in this grupo. So pasok ta sa una nga property. So let us proceed the second property. In the second property, ang giingon diri daw ang natay tulo ka elements nga A, B ug C naa daw ni group. Dayon naa daw ni group di na sa equal. Dayon kung ato daw i-perform nga star o ana B star C equal daw siya sa A star B ana mo na siya ay associative. So we have using the Keyless table, no? We have the elements, mag-select lang kung tanig pwede po 0, dayon natay elements nga 0, dayon 3, dayon 2. Much better ato isang ikuan nga sunod lang natin siya. So natay 0, dayon natay 1, dayon natay 3. O datay tulong element. So kung associativity kung pareha daw sila result. So 0 since our binary operation kini nga star dili na statong gamit kay we use the specific binary operation mo na ang addition. So 0 plusan daw og 1 plus 3 equal ba daw sa 0 plusan equal ba daw sa 0 plus nga 1 nga plusan pagyud og 3 equal daw sige daw by using the Achilles table. So by using the Achilles table di ta magbutbuot og perform solve diri ta magbase sa Achilles table. Kini daw 0 plusan og 1 plus 3. 1 plusan og 3 is equal to 0. Dili ta magbase sa Achilles table nga sayo pa ta kay 1 plus 3 4 na. But ila Achilles table na magutay gisunod dari. Wala na akong cursor. 1 plus 3 is equal to 0. 0 daw na siya. 0 plus 1. 3 daw 0 plus 1. 0 plusan 0 1 plus 3 1 plus 0 plus 1 siya. 0 plus 1 0 plus 1 equals 1 daw na siya. Dayon 3 na siya. Diba pag tanaw na to is dili isa equal but ato ning isolve equal ba kung equal siya that is the associative. So meaning our group is pasok ang the second property. So 0 plus 0 using the Achilles table 0 plus 0 equals 0. Diba? Kung itong itis kung equal bigay daw siya. Dayon 1 plus 3 daw. 1 plusan og 3. Diba 0? So equal siya. So meaning associativity pasok siya. So the second property is pasok is satisfied in this group nga Z mode, the set of integers modulo 4. Let us proceed in the third one property. The third one property says nagkanayon siya nga ato nang ikatulo. Ito nang gidilit ang number 2 kay di na maig ko maglisod nako. So ang inverse daw. So inverse. Diba the identity? Diba the identity here is 0? Diba 0? 0 plus 1, diba 1? 0 plus 2, diba 2 na siya? 0 plus 3 equals 3, diba 0 is the identity of addition? So 3. So meaning we have the meaning not tayo identity. How about inverse? No, inverse. How about inverse? Na daw inverse, we give back 0 daw. So di ba ang 1 unsa inverse sa 1? Dasod po addition di pa sa negative 1. So dili na siya mao kay we are now in a certain group man siya. So the inverse of 1 is nga mag-result siya og 0, meaning 1 plusan og 3 mo na ang inverse. 0. 3 ang iyang inverse sa 1. Then about sa 2, na daw tay inverse, so meaning pasok siya. 2 inverse niya kay 2. Under the modulo form sa 0. So meaning na daw inverse. So pasok ang iyang inverse. So at this time, so the four properties are satisfied in this group, in a certain group. So we can say that this certain group is really group good DI. So let us proceed. So we're going to test the subgroup. Na subgroup na punta. So now we talk about the subgroup, no? Kung this three important points nga mo satisfied sa given group is a really subgroup in the mother group kinangakindaan nga grupo. So meaning we have the subgroup containing the element H is equal to containing the elements 0, 2. Subgroup di ba kung ano siya subset, no? Pasok ang una nga important points. H is a subset of Z. So meaning kining H kining 0, 1, 2, diba anak siya sa 0, 1, 2, 3. So that is H is a subset of J. So check na siya. Okay. Meaning H is a subset of J. So check na siya. H is a group. So H is as a group. So we have the four, as I said a while ago, we have the four characteristics or properties nga makaingon tag ang group nga grupo gina nga kana nga grupo ha. Is that certain group is a really group. So dili na nako kuan kay dugay na kaayo, malangay na kanta, is time consuming. So makuha na tayo, kamo na bahala kay siguro nakasabot na sa pud mo. H and G use the same binary operation. So what is the binary operation being used in this kining example, diba? As I said a while ago, is the addition as the binary operation used in this example. So meaning H and G use the same binary operation. Di ba plus siya? 0. Kini nga keyless table. The same na itong ganyan akong gisolve. 0 plus 0 equals 0. 0 plus 1 equals 1. Di ba addition siya kini? 0 plus 0, 0 siya. 2 plus 2 siya. 0 plus 2 equals 2. 2 plus 2 equals 4. Modulo 4. 0 siya. Same. This G, kini nga, kung siya, subgroup ni siya, kini nga elements, subgroup ni siya sa G. So, sa G mod 4. So, meaning, H is a subgroup. H is a really subgroup in a group G. Dayon, ato yung itis niya kung associative, kung naba siya associative kay according ani nga second nga important point nga group siya associative, napon siya napon siya closure, na siya identity, napon siya inverse. So ako kung ikuan nato niya, kung ikuan niya is ako nang I'm going to select the associativity kay listen siya. 0 plus 0 daw plus 2 and 0 plus 0 plus 2 equal ba daw siya. So dili ta maglantaw na. 0 plus 0, 0. Ato iguanan to, bring down to. Kini pa 0 plus 2. 0 plus 2 equals 2, no? 0 plus 2, 0 plus 2. So ang 0 plus 2 equals 2 and 0 plus 0 plus 2 gyapon equals 2. Sakto. So meaning this is so kini nga kuan, this one is equal to this one. So meaning we have the associativity. So we are done, no? We are done in defining what is a group and what is a really subgroup and what is a really group. Good. So let us proceed. So we are done. So let us proceed in the second topic. Theorem 7.3.1. The SYLOW's first theorem. Let G be a finite group of order P to the raised to R times M, where P is a prime, R and M are positive integers, and P and M are relatively prime. Then the group G has a subgroup of order P to the raised of K for all K greater than or equal to 0 but less than or equal to R. So at this point, I will be I'm going to expound how this theorem, which is theorem 7.3.1, all about. So we have the finite group G. Then the order of the finite group G is that P to the raised of R times M. That order, which is P to the raised of R times M, that is the number of elements, that is the cardinality of the certain finite group G. Then P is a prime. So when how can we say that a certain number is a prime number? So according to the definition of prime number is a positive number greater than 1, and it has only two factors. It has only two factors, plus as 1 and itself. Then P and M are relatively prime. So how can we say that the two numbers are relatively prime? So the greatest common divisor of the two numbers is equal to 1. Then that finite group G has the order P to the R times and then has a subgroup. So let it be a subgroup of G, and it has the order of P to the of K for all K greater than or equal to 0 but less than or equal to R. If we can consider that the value of R here in our mother group, kinadak-an nga group nga mo niyang the group G, P to the raised of R times M. So we can So I'm going to consider that the value of r is equal to 1. So the possible values of r in our subgroup H as the order p to the raised of k. So our r here in this can be for all k greater than or equal 0 man but less than or equal to r, so it will becomes on k greater than or equal to 0 but less than or equal to 1, since our value of r in the finite group G is equal to 1 man. So now I'm going to now I will be presenting my second presentation, because I'm going to show you the what are the examples of prime numbers, and the numbers are relatively prime. So let us present. So we are now in my second presentation. So here I will be discussing what is a prime number as well as what is a relatively prime. According to the definition of prime number, it is a counting number greater than 1 and that has exactly two factors, including itself and 1. For examples, 2, 3, 5, 7, 11, 13, 17, 9, 23, and these are some possible examples in prime number, because a number 2, it is a positive number greater than 1, and number 2 has only two factors, including 1 and itself, it is 2. As well as for the number 3, 5, 7, 11, 13, 17, 9, 23, and daghan pa. Then we are now in the relatively prime. So how does it mean by the word relatively prime? How these numbers becomes a relatively prime, no? The definition of relatively prime: the two numbers are said to be relatively prime if the common factor between the numbers is 1. So if the two numbers are said to be a relatively prime if the two numbers has only a greatest common divisor, it is positive 1. For example, 2 and 3, the greatest common divisor of 2 and 3 is equal to 1. Also for example 5 and 8, the GCD of 5 and 8 is equal to 1. So these are some of the possible examples of relatively prime. So we are now in the first proof of SYLOW's first theorem, which is theorem 7.3.1. So here is a proof of this theorem. Let the order of the group G is equal to n or equal to p to the raised of r times m. So this symbol is the cardinality, or so we say the absolute, but this concept that is not the absolute value, but it is the number of elements, the order of the group G is equal to n, is equal to p to the raised of r times m. We prove the result by induction on n. If n is equal to 1, then r is equals to 0. And the identity element is the required subgroup of order p to the raised of r. Why? If n daw is equal to 1, then, so nag-conclude siya nga r is equals to 0. Then nag-asumungod ta nga the order of the group G is equal to 1 daw. Kaya now, if n is equal to 1, so our subgroup na p to the raised of r, so meaning any numbers that has 0 exponent, that is why r is equals to 0. Any numbers has 0 exponent, automatically the result is equal to 1. So the identity element is the required subgroup of order p to the raised of r. That is why if n is equal to 1, so automatically r is equal to 0. Suppose the result is true for all groups of T of order less than the order of the group G. If r is equal to 0, then the identity element is the required subgroup of p to the raised of r. we now assume that R is greater than or equal to 1. First, suppose P divides the order of the center of the group G, where G of G is the center of G. So, unsa na pud ni ang the center of the group G? So, according to the definition of the center of the group G, if G is a group, then the center of the group G is equal to the set containing the elements A is an element of G such that AB is equal to BA for all B as in G. So meaning there is an element in a group G that commutes all elements in G. So even though this topic, the center of the group, has been discussed from the previous chapter, so this is touch ni gamay sa kuha, so I'm going to explore this later. I'm going to expound this later in my second presentation about the center of the group. Let us proceed. Since P divides the order of the center of the group G, there exists A is in the center of the group G such that the order of an element A is equal to P by Cauchy's theorem. So recall from the definition of Cauchy's theorem. If G is a group and P is a prime number dividing the order of the group G, then G contains an elements of order P. That is the definition of Cauchy's theorem from the previous chapter. Let H is equal to the subgroup generated by A. So, nana po yung subgroup generated by A. So, meaning, E here is the generator. Then, the subgroup generated by A is equal to H. So, this generator A, nag-contains po na siya elements. The subgroup generated by A is equal to the nag-contain po na sa elements under the binary operation of a certain group. So later I'm going to discuss this what is generator? Unsa ang generator daw? So unsa daw ang generator? So I'm going to expound this aspect in my second presentation. Then H is a normal subgroup of G. Nanapod ang normal subgroup. Then H is a normal subgroup of G since A is an element of the center of the group G. So how does it mean unsa ang normal subgroup? So according to the definition of a normal subgroup, if H is a normal subgroup of G, then the left coset mao na ang EH is equal to the right coset mao na ang HA. Then A is an element of the group G. So later I'm going to discuss the center of the group and the normal as subgroup. Now let us proceed. Now the order of the quotient group is equal to P to the raised of R minus M times minus 1 times M. Hence, by the induction hypothesis, the quotient group has a subgroups K sub I slash H of order P to the raised of I for all I is equal to 0, 2, R minus 1. Then the identity element H K sub 1, K sub R minus 1 are the subgroups of G, of the group G of the required order. Now suppose P does not divide the order of the center of the group G. Consider the class equation. It can be read as the summation runs over a complete set, possibly empty, of distinct conjugacy class representative which do not belong to the center of the group G. From the hypothesis, P divides the order of the group G if P divides the index of the centralizer of A in G for all A does not belong in the center of the group G, then from the class equation it follows that P divides the order of the center of the group G, a contradiction to our assumption. Hence, There exists E does not belong in the center of the group G such that P does not divide the index of a centralizer of A in G. So now, the order of the group G is equal to the index of centralizer A in G times the order of centralizer of A. This implies that P to the power divides the order of the centralizer of A. Since A is an element of centralizer of A, comma, the order of the centralizer of A greater than 1. Also, the centralizer of A does not equal to G since A does not belong to the center of the group G, hence the order of the centralizer of A less than the order of the group G. Thus, by the induction hypothesis, centralizer of A has a subgroup of order P to the of I for all I greater than or equal to 0 but less than or equal to R. Hence, G has a subgroup of order P to the of I for all I greater than or equal to R. So that is the end of our proof in the theorem, in the first theorem, which is theorem 7.3.1. So let us proceed in the second proof of the SYLOW's first theorem, which is theorem 7.3.1. If R is equal to 0, then the identity is the required subgroup of order P to the of R. As I said a while ago, the identity element is considered as a trivial subgroup of every group. So that is why that if R is equals to 0, if R equal to 0, then the identity element is the required subgroup of order P to the of R. Suppose R greater than or equal to if R greater than or equal to 1. Since P divides the order of a group G, G has the subgroup of order P by Cauchy's theorem, as I said a while ago, the Cauchy's theorem. We now show that G has a subgroup of order P to the of I, then G has a subgroup of order P to the of I plus 1, where I greater than or equal to 1 but less than or equal to R. Suppose G has a subgroup H of order P to the of I, where I greater than or equal to 1 but less than or equal to R. Then H is a proper subgroup of G. By workout exercise page 176, the index of subgroup H and the normalizer of H is congruent to sub P, the index of the subgroup H in NG. And H does not is not equal to the normalizer of H, since P divides the index of the subgroup of H in G. It follows that P divides the index of the subgroup of H in normalizer of H. That is, P divides the subgroup divides the quotient group. Thus, the normalizer of H, the normalizer comma H I slash H has a subgroup K slash H of order P by Cauchy's theorem. Now the order of K is equals to the order of the quotient group. The order of the quotient group times the order of the group H is equals to P times P to the rest of I is equal to Pi plus 1. Therefore, K is a subgroup of G of order P to the rest of I plus 1. The result now follows by induction. That is the ends of our proof in theorem 7. The second proof in theorem 7.3.1. So it is really hard to understand and comprehend this theorem because this is proving this course is more on a word or statement form, so that is not it is not easy to understand, and it is really difficult for me to to explain, but in my second presentation, I I have there the kanang the examples, are one of the examples that is arbitrary. So arbitrary lang, one of the possible examples of this theorem. So now we are now in the example in the theorem 7.3.1. So the theorem is, it says that the theorem says natay grupo nga the order of G, the order of the finite group G is that P to the rest of R kini P to the rest of R times M. So I give an example, no? So don't focus basta nakaingon mo nga kini lang example, pwede sa 1 million ang order niya. Basta ning sunod sa condition nga P prime gid ang P gid prime na say prime ni kini siya, din kini sa positive integers, din kini og kini niya kining M and P are relatively prime. So pwede pa sa 1 million ang ihang cardinality or the order of the group. Pero nagpili ko og J modulo the set of integers modulo 6. So we have the 6 elements 0, 1, 2, 3, 4, 5. So the order of the group G modulo 6 or the finite group countable sa, di ba, maihap siya, countable sa finite group ni siya. So meaning natay ko the P is a prime daw. So 3 is a prime. 1 is a positive integer and 2 is positive integer, but 2 and 3 are relatively prime. So pasok siya sa condition. Pwede ni siya nga kini nga grupo. Arbitrary lang ni siya. Then natay subgroup daw. Kini daw siya dato subgroup nga P to the rest of K. It is a subgroup of J where ang H daw nasa order nga P to the rest of K. Ang mo ni subgroup dayon P to the rest of K for all K greater than or equal to 0 but less than to equal to R. So meaning our possible nga subgroup di ay P to the rest of K since our kini nga condition is that our R is equal to 1. So meaning mahimo na ni siyang atong value of K pwede pod siya nga K greater than or equal to 0 but less than or equal to 1. Since our R here, our value of R is 1 man siya. So meaning 1 na ni siya. So meaning kini nga prime nga 3 kini siya always natin gamiton kay P prime gani P prime ni siya prime, so dili pod P pod, so dapat kini tong gamiton 3 to the rest of 1 is equal to 3. So natay subgroup daw nga order of 3. So meaning the order of 3 dinabot sa usa ka dre nga P to the rest of K pod nga atong second subgroup nga 3 to the rest of 0 kay 3 to the rest of 0 is equal to 1 man. So meaning nga naka 0 man tada because pwede pod sa 0 kay greater than or equal sa 0 ang value sa K. So meaning 0 pod siya. Dayon kini nga kuan kay nga subgroup P to the rest of K to the rest of 1 so is equal to 3. So don't confuse about my example because nagpili lang ko ako ng for us to visualize what the theorem talk about. So meaning atong first nga subgroup is 0, 1, 2. Ini nga subgroups ini nga elements na bas 3 ang elements but kini gasunod sa ano, di ba? 0, 1, 2. Gipili lang nako ni sa 0, 1, 2. Pwede po sa 3, 4, 5, 1, 2, 3 basta 3 elements ang order niya, ang order sa subgroup gina siya. Dayon kini nga second subgroup 0 pwede po sa 1. So meaning 1 man siya, so nasa siguro na po sa pwede sa pod 2. Muna kung gipili siya pero arbitrary lang siya, pwede possible mga one of the possible examples arbitrary sa each the second subgroup ngani dayon pwede sa ilis ng 2, 0 pwede po 5, di ba subgroup ni siya sa atong finite group G. So we are now in my second slides, as a while ago, I'm going to explain the center of a group. So the definition of a center of a group, if G is a group, then the center of G denoted by G of G is given by G of G is containing the set A belongs to the group G such that AB is equal to BA for all B is an element of G. So meaning there is an element nga A nga commute the all elements in a group G. Now for all elements in a group G, kat mo na ang B. For example, we have a group, we have a group at G mod 4, G mod 4 or G a set of integers modulo 4. Then The Z mode 4, we have the elements 0, 1, 2, and 3. The meaning, so we're going to perform this using the Keras table, because Keras table is very useful and essential in the group theory. Then, this is under the binary operation of addition. 0, 1, 2, 3, addition 0, 2, 3, 1, any 1, 2, and 3. Zero plus 0 is 0, 0 plus 1, 1, 0 plus 2 is 2, 3, 1, 2, 3, 0, 2 plus 0 is 0, 2 plus 1, 3, 2 plus 2 is 4, modulo 4, 0, 2 is 5, 5, modulo 4 is 1, 3 plus 0 is 3, 4 modulo 4 is 0, 3 plus 5 modulo 5 is 1, 3 plus 6 is 6, modulo 4 is equal to 2. Okay, 3 plus 3 equals 6, modulo 4 equals to 2. So we're going to determine what is the center, no? This group, what is the center of this group, no? G, the center of the G4, no? The center, no? The center of a group nga mao ang G4, no? Ang center niya is 0. Muna itong example to, muna ang A, ng element G, 0. 0 siya. Mga 0 man. 0 plus 0 equals 0. Because the identity element in a group is always the center siya sa group. Then how about 1? 1. How about 1? This is 1. 1 is a 1. So 1 plus 0 equals 1. Then 0 plus 1 equals 1. So commute. Pasok ang 1. 1 plus 2 equals 3. Then 2 plus 1 ug 1 equals 2 plus 1 ug 1 equals 3. So commute yapon na siya. So 2. 2 pwede ang 2. 3 daw. 3 plus 0 equals 3. Then 0 plus ug 3. 3. Kaya sabi diri sa kuha ang definition niya, EB is equal to BE. Commute, so meaning pasok ang 3. How about sa kadaw 3 plus 2? 3 plus 2 equals 1. Then 2 plus 3 is 1. So meaning is 3. So meaning the center of this group G modulo 4 is the group itself. So that is the the center of the group G mod 4, the set itself, or the elements itself. That is the definition of the center of the group. So we're now in my second presentation. So I'm going to talk about what is the generator. So but before that, I'm going discuss first the cyclic group, because cyclic group is nasa relation, no? Cyclic group has the relation into the generator, because a group is called a cyclic if there is an element. So according to the definition of a cyclic group, a group G is a cyclic if there's an element A belongs to the group G such that G is equal to the subgroup generated by A. But this A is a generator. So we talk about the generator. So according to the definition of generator of a group G is an element of A belongs to the group G such that J is equal to the subgroup generated by A. So that is the generator. So we talk about what is a cyclic. So a cyclic daw, if there's an element daw, for example, we have the group, no? We have the group here, no? J mod 3, the set of integers modulo 3. So we have 3 elements. If naa daw ani nga 0, 1, 2 nga nada sa subgroup generated daw ani under the binary operation of addition, tawgo na to na siya og generator. For example, a generator 0. So 0 here, no? 0. 0 is the identity of addition. So muna niya ang element 0. Ang generator nga 1, no? Subgroup generated by 1, no? So 1 plus 1 equals 2. 2 plus 1 equals 3. But modulo 3 is equals to 0. How about 2? Oh, no. 2 here. 2 plus 2 is equal to 4. Modulo 3 is equal to 1. 1 siya. 1 plus 1 equals to no. It is no, hindi apply. 1 plus an og 2 kay 2 man siya is 3. Modulo 3 is equal to 0. So meaning this group is a cyclic group because according to the definition of a cyclic group, if naa daw element daw na sa group, muna atong group nga G mod 3 nga equal daw ang element daw ani is equal to the subgroup generated by A. Suppose natay duha ka element kini, oh? Because the orders does not matter. So 1 2 0. So 1 2 0 is equal daw sa group nga G. So meaning the subgroup 1 is equal to the subgroup pod nga generated by 2, equal daw siya sa group nga G nga mao ang G mod 3. So this group is a cyclic group. Then we talk about the generator. So the generator of this group G mod 3, the set of integers modulo 3. So we have the two generators. We have 1 and 2. These are the generators of this particular group because the subgroup generated by 1 containing the elements nga 1 to 0 are also elements in a G mod 3 muna equal, no? Muna tawag subgroup. Ang tawag cyclic kung na ang group daw niya is equal daw sa subgroup generated by A. So, atong 1 is equal siya then kinipod 2 pod equal pod siya. So meaning we have two generators in this particular group. Am I clear? Di ba? Sige, clear ko. Kay these are the subgroup, these are the generator 1 and 2. Muna yung sabat ang generator og cyclic nasa relation kay kung si cyclic nasa generator. So ito generator dito gina sa cyclic na topic. So cyclic group. So this group is, we can conclude that this group is cyclic group because since there exists an element nga 1 and 2 nga nag-generate nga kini nga grupo. Therefore 1 and 2 are generators of this group, which is G mod 3, set of integers modulo 3. So that's the end. So we talk about right now the what is a normal subgroup. The definition of a normal subgroup: H is a subgroup of G. Kini nga sign is a subgroup. H is a subgroup of G. Is called a normal subgroup if the left coset mo ni ang GH is equal to the right coset mo ng HG, that G belongs to the group G. The small letter G is belong to the element that belong to the capital letter G. So we have the group G mod 4 0 1 2 3. So our subgroup is containing the elements 1, 2. Kini daw is a subgroup ani daw pero normal subgroup po din siya. So we are going to test that, no? So mo sa 0 plus 1. Ngano na 0 plus ano? How can I come up this 0 plus 1? Because 0 according to the definition of a normal subgroup G is an element of the group. Muna atong group G. So meaning our G is 0. Pwede po 1, pwede po 2, pwede po 3. But it is time consuming. Ako lang gamay lang examples na kung gisulat dire. Dayon 0 is an element of the group G. Muna yung group G. Then ang 1 is the elements in the group, in the subgroup H. Muna 1, muna 1, muna bisa tong 1. Muna ang left coset, mo ang right coset. Then I'm going to perform this one. 1 is equals to 1 gamit ang under the binary operation of addition. Gamit kayo ang binary operation aning nga group. And then so we have the another element of the in the small letter G na nasa dako nga G. Mo ni ang 1, di ba? Belongs to the group G, mo na G mod 4. Then itong 1, mo ni 1, mo ra gyapon nato ni siya sa element of the subgroup H. Then I'm going to perform this one is pareha ra gyapon siya. So meaning, di ba equal sila? Di ba matawag sa normal subgroup if equal ang left coset to right coset? Mo ni ang left coset, mo ni ang right coset, left coset, right coset. Dayon, so we have the example nga 2, di ba? Small letter di ba G, small letter G belongs sa group G. Atong G ini sa nagrepresent ani nga kini nga elements. Ning kini nga G mo ni ang entire no sulod ani. So we have the 2. We have 2 din atong 1 is naara H ang left coset and the right coset is equal to 3. We're going to perform this one taman sa nga 3 inapodita ito balik sa 0 plus 2 or 2 plus 0 equal yapon na siya. So meaning this subgroup H, the subgroup H in G, H is a subgroup in G, is called a normal subgroup if the left coset is equal to the right coset if G is belongs to the group G. So meaning this one, this examples kayo na satisfied ni siya bisan ipadayon ninyo og one because it is time consuming because taas na kayo. So this one ako na siyang giputol mo yung ipakita ng gamay some sort of example regarding in the normal subgroup. So that's the ends of a discussion about the normal subgroup. So let us move on in the corollary 7.3.2. So this corollary is derived or came from the SYLOW's first theorem. So nakaka-up sa corollary ng 7.3.2. Let group G or let G be a finite group and P is a prime if P to the raised of n divides the order of the group G. Then G has a subgroup of order P to the raised of n. So, ano siya? Tinuod ni siya. So, for example, if the finite group G na contains an elements nga nasa order nga P to the raised of n times n from the first the SYLOW's first theorem, and P is a prime number. Diyon, for example, we have the group nga na contains of elements six elements, no? We have the finite group G. The cardinality of the finite group G is equal to 6. Then P is a prime. P to the raised of n divides the order of the group G. Then G has a group of order P to the raised of n. So our finite group nasa order nga P to the raised of n times P to the raised of n times m. So meaning, so we have a P to the raised of n times m. Atong P is a prime number, n and m are positive integers. So meaning, P, we are going to put the value in P is 3 because 3 is a prime number because 3 there are only two factors, which is positive 1 and itself mo na ang 3. That is why the 3 numbers is a prime number. So 3 to the raised of, so atong order sa finite group G kay P to the raised of n times m. So 3 to the raised of 1 because n and m are positive integers. So any positive integers pwede na ito magamit sa values of n and m. So 3 to the raised of 1 times 3 to the raised of 1 times 2 because the condition in the theorem 7.3.1 n and m are relatively prime. So 3 to the raised of 1 times 2. So 3n 2 is a relatively prime because the greatest common divisor of 3 and 2 is equal to 1. So pasok siya sa condition sa SYLOW's first theorem nga P and M are relatively prime. So 3 to the raised of 1 P to the raised of 1 times 2. So 3 times 3 to the raised of 1. So meaning 3 times 2 is equals to 6. So natay F if P to the raised of n divides the order of the group G. So condition na siya. That we say F it is nag-establish na siya og condition p to the rest of n. So our finite group G nga nasa order nga p to the rest of n times m. So our p to the rest of n times m mo na ang 3 to the rest of 1 nga nag 3 to the rest of 1 times ato. So 3 to the rest of 1. So if 3 to the rest of 1 divides the order of the group G, which is the order of the group G is equal to 6 because our finite group is 3 to the rest of 1 times 2 is equals to 6. Mo na ang the order, the cardinality of the group, the finite group G. You see the order, the number of elements in the group G, in a certain group. That is the order. Dili na sa absolute. That's not absolute. That is the order, the cardinality, the number of elements in the finite group G. So as I said a while ago, kung ato ang finite group G nga 3 to the rest of 1 times 2, so ang result, ang ihang equivalent na is equal to 6 ang resulta na niya. Kung f p to the rest of n, so di ba atong 3 to the rest of 1 mo na ang 3 p to the rest of n times m. So p, our not a subgroup nga pn daw kung mag-divide sa order of the group G. It's really difficult in it is really hard to discuss ngayon a virtual mode of learning. Pero sige lang. If p to the rest of n daw, so our mother group, okay, kinadak-an nga group na to, muna ang finite group G, muna itong kinadak-an nga group. Kini nga subgroup na pn, anak na ni siya sa our kinadak-an nga group muna ang G, the mother group. Sa set pa di sa mother set. Kung pn is a subset, wala siya kung pn. So group sa algebra man ta, so wala siya subgroup o group. Then if p to the rest of n, so natay 3 to the rest of 1 times 2 muna to ang finite group nga G is equal to 6. Kung natay subgroup nga pn daw, 3 to the rest of usa atong gigamit na to sa group na to is 3 to the rest of 1, di ba? 3 to the rest of 1 is equals to 3. Is equal to 3, di ba? 3 divides 6, di ba? Sakto siya nga condition nga 3 divides 6 or 3 is a divisor of 6. Is it true or not? So tinuod gid siya. 3 divides 6. So meaning 3 is a divisor of 6 because this divisor siya. Ang 3 is divisor siya sa 6. So naka-conclude siya. Then group G, mo na to finite group G nga order p to the rest of n times m na asa subgroup nga p to the rest of n. Mo na siya that is the muna siya gipasabot sa corollary 7.3.2. We are now in the 7.3.3. Let G be a finite group and P a prime. A subgroup P of G is called a SYLOW P subgroup of G if P is a P subgroup and is not properly contained in any other P subgroup of G. That is, P is a maximal P subgroup of G. So we have the example, no? So we are now in the example 7.3.4. The symmetric group S3 has 3 SYLOW subgroups, namely, so we have the 3 subgroups of the symmetric group S3. So meaning, this group is a permutation group. The symmetric group is also known as permutation group. This S3 is the group of permutation on the set S with 3 elements. So in this group, generally natay we have 3 elements. But since this is a permutation group, these elements, the S sub 3 is the group of permutation in the set S with 3 elements. So we have 3 factorial ways. So we have the 3 factorial ways that we can permute, permute the elements of the same. We have a 3 factorial ways that we can permute the elements. So paunsa ni nga tulo ka subgroup sa paunsa ni nga symmetric group S3, that is our group. Then the symmetric group S3, the permutation group S3 has 3 the SYLOW 2 subgroups. You see the SYLOW 2 subgroups these subgroups contains only the two elements, or the order of the subgroup. The order of the subgroup is 2. Every subgroup of this S3, because since this is SYLOW to subgroups, the contents of the elements, the cardinality of the subgroup is equal to 2. So kindly take a look in the screen, no? We have 3 subgroups, no? Namely the H sub 1, the H sub 2, and lastly the H sub 3. No, kindly take a look in the screen. The H sub 1, we have 2 elements, no? H sub 1 containing the set, the parentheses 1 maps to 1, 2 maps to 2, 3 maps to 3, comma 1 maps to 2, 2 maps to 1, 3 maps to 3, as well as for the second subgroup, as well as for the last subgroup. So this 3 subgroup contains of order 2. So meaning duha ka elements yun, duha gid ka elements, because the 1 maps to 1, 2 maps to 2, 3 maps to 3 is equivalent for one element, for one element. How about the 1 maps to 2, 2 maps to 1, 3 maps to 3 is another one element. So the H sub 1 contains the 2 elements, as well as for the 2, also for the as well as for the second subgroup, as well as for the last subgroup, is the H sub 3. Thus, a SYLOW subgroup of a given group need to be unique, because it is unique because the SYLOW to subgroups contain na siya og 2 elements, dili na siya pwede 3, because the SYLOW to subgroups pwede po na siya SYLOW 3 subgroups, but here the example is specifically the SYLOW to subgroups. But so this time, so let us proceed in my second presentation, because I will be discussing how these 3 subgroups arise or exist. Kay ga gibutang naman na sa largo siya. So how can we determine these 3 subgroups? Or so also I will be discussing the symmetric group S3, no? The symmetric group S3. 3 siya ka elements based on that, pero so 3 siya ka elements, but naasay tinuod nga elements is the 3 factorials, because 3 factorials, because since this is permutation group, 3 factorials, 3 times 2 times 1. So 3 times 2 equals 6, 6 times 1 is equals to 1. So basically all elements in the symmetric group S3 containing the set of elements containing the 6 elements, no? So let us proceed in the second presentation for us to understand better what I'm talking about. So let us now, I'm going to expound on the example of 7.3.4. The symmetric group S3, or shall we say the permutation group, or the symmetric group is similar, no? So this S3, no, this S3 symmetric group S3, no, shall we read this one, is that group of permutation and the set S with 3 elements. So these 3 elements, since it is a permutation group, we have 3 factorials that we can permute the elements, no? So meaning 3 factorials, 3 times 2 times 1 is equal to 6. So meaning kini nga group, the symmetric group, we have 6 elements, di ba? Kindly take a look in the screen. We have 6 elements, no? We have the 6 elements. Na type group of permutation. Ato na isulat niya ang 1 2 3. Kini nga 1 2 3 daw maps daw ni siya ika-unom, no? We have a 3 factorial ways that we can permute the elements 1 2 3. So since this is permutation, maps daw ni siya sa ika-unom nga ways nga paagi. So una nga paagi 1 2 3, di ba mo pwede sa map the identity 1 2 3 1 2 3. Ang 1 may maps to 1, 2 maps to 2, 3 maps to 3. So meaning as kini siya, that is map pod ni siya. Dayon this element, this one, we can write this one into the in the cycle notation. This is called the cycle notation. In solving in finding the SYLOW to subgroups. So we should transform this one into cycle notation. How can we perform this one into the cycle notation? Since this is 1 maps to 1, 2 maps to 2, 3 maps to 3, so meaning the identity being maps is ang kaugalingon. So that is a identity, dili na siya, it is not 1, it is the identity so kini 2, 3. How can we solve this one? Ngayon mo sang 2, 3, di ba? As you can see, 1 ming maps to 1. So nasa 1 na siya dire, but if the cycle notation 1 ang iyang element, dili na siya pwede isulat kay, because it is obvious naman siya, good, klaro naman siya. So meaning 2 maps to 3. So kini 2 ming maps to 3 daw, 2 ming maps to 3. Then 3 pod 3 ming maps to 2. Mimbalik ra na siya, 2 ming maps to 3, 3 maps to 2. So that is why it has become 2, 3. Then 3, 1, 2, 3, 1 ming maps to 2, 1 ming maps to 2, 1 ming maps to 2, 1 ming maps to 2. Ang 2 po daw ming maps to 3. Then ang 3 po daw ming maps to 1. Wala na siya gisulat kay mimbalik man siya, 3 maps to 1. That is why 1, 2, 3. Right? Then the fourth one, kining 1, 2, 3 ming maps to 1 ming maps to 2, 2 ming maps to 1, 3 ming maps to 3. So meaning 1 is i-map niya ang 2, maps dito sa 2, 1 ming maps sa 2, di ba? As you can see in the screen, 1 ming maps to 2, 1 ming maps to 2, din 2 po daw ming maps to 1. So meaning dili na sa isulat ring 1 kaya na may 1 dire, 2 ming maps din balik naman siya. So parehara na sila, 1 ming maps to 2, 2 ming maps to 1, so 3 ming maps to 3. Pwede na sa isulat ang 3, but according to the definition of the cycle notation, if there is a cycle notation nga nagcontain a single element, dapat walaon na siya kay understandable man sa mananawala ang 3. Then kini 1 to 3, how about then 1 to 3, this is the original element, 1 ming maps to 3, 2 ming maps to 1, 3 maps to 2, so 1 ming maps sa 3, 3 pod ming maps to 2, no? 1 ming maps to 3, ang kini nga 3 pod ming maps so puto to mning butang siya 2, then ang 2 pod ming maps to 1, so ming balik siya. So mibalik siya, wala na siyang gisulat diri nga to. Di na sa kinalaguan sa kay maridandan siya. So dapat 1 ming maps to 3, ang 3 pod ming maps to 2, so 3 maps to 2 nang gibutang rin din ang 2 ming maps to 1, so mibalik siya. That is why this one becomes this one, 1, 3, 2 ang cycle notation niya. Then 1, 2, 3 og 3 to 1, 1 ming maps to 3, di ba? 1 ming maps to 3, so meaning 1 ming maps to 3 to ming maps to 2. So dili na sa pwede sulat kay pwede sa sulat pero dili na sa walaon na siya. As I said a while ago, the cycle notation is containing one element, so dili na sa kinahanglan. So 3 ming maps to 1, so balik siya 1 ming maps sa 3, then ang 3 po daw kini nga 3 ming maps to 1 daw, so balik siya. That's why this one become this one. So the symmetric group S3 has 3 SYLOW to subgroups, because how many elements in how many groups are in this one? How many groups containing 2 elements, and because SYLOW to subgroups nag-include na siya, nag-contain na siya og 2 SYLOW subgroups kay the order of 2 elements nga nag-order nga 2 na sulod nga duha. So meaning 2, 3, 1, 2 and 1, 3. That is why the SYLOW to subgroups, we have 3 subgroups. 1, 3. Kini nga 2, 1, 3. 2, 3, 1, 2, and 1, 3. These are the subgroups of the symmetric group S3 in order to, or the SYLOW to subgroups. Then every groups has the subgroups of the identity. Dapat mo nang isulat sa identity. Di ba identity ni siya, di ba? The identity I mo nang isulat niya I 1 I dayon 1 2 kay kini siya diri nigikan kini 1 2 3 og 2 1 3 mo ni siyang 1 2 mo 1 2 siya dayon every groups man god kay has the subgroups of identity. Man tawag na ganiya as ko trivial subgroup. Dayon kini nga 1 2 3 1 2 3 map itself, so meaning is the identity ni siya. Din kini pa sa identity, din kini siya is 1 3, so diri ni ko 1 2 3 3 2 1 mo ni siya 3 2 1 mo nang na 1 3 siya. As I said away go, as what I have explained about the cycle notation, yun sa siya pagsulat. Dayan 1 2 3 1 3 2, so meaning 2 3 siya kay diri ko 1 2 3 1 3 2. So cycle notation siya. Identity mo nga I ni tanan kay this kini nga element maps the identity. Map itself mo na identity siya. All right? So the symmetric group S3 has three the SYLOW subgroups has 3 subgroups because by this cycle notation we have the subgroup here, we have the subgroup here containing 2 elements, 2 3 1 2 mo nang 1 3 mo nang natulo siya. So to better understand for us to better understand nga giunsa from this cycle notation, giunsa I'm going to explain this in the second slide. In the following slide mo ni siya kini siya. So giunsa siya, di ba? As I said a while ago, 1 2 3 1 2 3, di ba, maps sa iyang kagulingon mo ng 1 2 3, so wala na siyang sulat, identity na lang na siya. Di kini pod 1 2 1 may maps to 1, 2 maps to 3, 3 may maps to 3 2, so 2 ang 1 may maps to 1, so 1 di sa kinahanglan 1 may maps to 1 ra na siya. Then kini sa 2 may maps sa 3, ang 3 pod may maps to 2, so mimbalik siya. Mimbalik 2 may maps to 3 maps to 2. That is why nga mo na ang cycle notation. This one is a product of 2 cycle notations. Din kini 1 2 3 2 3 1 1 2 3 siya. 1 may maps sa 2, ang 2 pod may maps sa 3. Pero ang 3 pod may maps sa 1, so mimbalik siya. So 1 2 3 gina sa cycle notation. How about this one? 1 may maps sa 2, 1 may maps sa 2. Ang 2 may maps sa 1, so mimbalik siya, lahi na po 1 may maps to 2, then ang 2 pod may maps to 1, balik siya, so 3 maps to 3, so 3 siya. This one is a product of 2 cycles. Dayon kini 1 2 3, 1 may maps sa 3, ang 3 po daw may maps sa 2, then ang 2 po daw may maps sa 1, so mimbalik siya, nunod na sa isulat sa 1 3 2 siya. Ini 1 2 3 3 2 1, so 1 ming maps sa 3, di ba? 1 ming maps sa 3, 1 maps to 3, and 3 ming maps to 1. So no need to write the 3 maps to 1 because this is already written in this version. So 1 3 na siya. Then 2 may maps to 2, so no need to write the 2 maps to 2 kadi na sa mao. This one is a product of 2 cycles. So kini siya is mo nang, as I said a while ago, mo nang don't confuse nganong nga naingon ani ni siya tungod kay 1 2 3 is a 1 1 2 3 mo na siya ganiha 1 2 3 then 1 2 3 mo na siya himong the identity kini identity din kini siya is nahimo sa 2 3 dayon kini pod siya 1 2 3 po ni siya 1 2 kini siya 1 2 ni siya resultant niya yung ipatunga nako ni kini po 1 2 3 ay kaning 1 2 3 og 1 3 2 1 trinigikan, so meaning 1 3 siya. So the SYLOW subgraph of the symmetric group S3, so the group of permutation on the set S with 3 elements. So we have the 3 factorials that we can permute the elements, so that mo na nga 3 factorial 6 1 2 3 4 5 6, we have the 6 elements gid bale. So dapat, so how many elements here gimuhat na tong cycle notation nga naay containing og 2 order nga 2 elements, nag-order og 2, di ba? 2 3, di ba? Duha siya 1 2 duha gyapon siya, di sa pwede 1 3 kay tulo man niya SYLOW subgroups man, so dapat duha gid siya. So meaning we have the 3 SYLOW subgroups sa group of permutation nga is 3. So that's, I have another definition of the SYLOW subgroups. Kini daw siya nga definition is taken from the YouTube definition. A finite group whose order is divisible by a prime piece to the rest of 1. So this definition is equal to the 7.3.3 same ra ni sila. Ako lang isang gikuha sa YouTube aron for us to better understand, no? That is to understand about this kato nga theorem nga 7.3.3. Kini daw siya is a finite group whose order is divisible by a prime p to the raised of 1 contains a SYLOW p subgroup such that p to the raised of 1 nagdivides the known order of a group G. Pero p to the raised of 1 plus 1 does not divide the order of the group G. So meaning nagkatungang mga SYLOW to subgroups, nagkuha ko og usa ato kini nga element 1 2 3 nagkuha kog nagkuha kog subgroups diri usa lang ka buok aron mapakita nako ninyo kini kini nga subgroup the subgroup sub 1 nagkuha lang kog subgroup ato dong ikuan na siya og mao na siya kung tinuod ba ni nga theorem kung mahimo na siyang SYLOW p subgroup. Now kung kini daw nga p sub 1 kung sa SYLOW p subgroup such that p sub 1 pero dili siya makuan mao nang makapermanent tag SYLOW p subgroup ina daw to, di ba to? Our H sub 1 is nasa duha ka elements, no? Duha ka elements niyo. Kini another element ni siya, kani lahi po siya another one element. So dapat ang ihang sulod ay ani nga the cardinality of this group is or subgroup nag-contains og 2. Then ang ihang meaning niya is p sub 1. So 2 is a prime ba ya? Prime. 2 to the raised of 1 divides the order of 6, di ba? 2 to the raised of 1 divides 6 tinuod. 2 is a divisor of 6, di ba? 2 is a divisor of 6. But ang 2 daw, kini but p mo na atong 2 1 plus 1 equals 2 mo nang 2 to the raised of 2 does not divide the order of the group G. Kay ang order of the group G is 6 man, di ba? 6 man to, di ba? 6 man to ang S3, the group of permutation or the symmetric group S3, 6 man siya. So tinuod ni nga definition, pasok ni siya kini samot na dito sa second subgroup o the last one subgroup kay tuloy ba ni ka subgroup. So pasok siya, therefore our answer is correct. But this definition is taken from the YouTube. So that's the end of this example.